to make things concrete and mathematically manageable, and so that we can have clean derivations to expose the theory, we're going to work with linear regression. Regression turns out to be simpler to work with, and linear models, are easy to mathematically manipulate. So let's have a quick review of linear regression, because that's the context in which we're going to make most of our discussion. Okay, so remember, in linear, in general, you have your original X space. So you have your data X1, Y1, X2, Y2, and so on up to Xn, Yn. Okay, and we're going to allow now for the nonlinear feature transform. So even though we are narrowing down to this concrete case of linear regression, you get immense power by being able to go to an arbitrarily complex, feature space using any feature transform you want. So, if you transform this data, remember you only transform the X values, and so this becomes a Z1, Y1. You don't transform the Y values, Z2, Y2, up to Zn, Yn. Okay, so this is the transform data. Now, when we went into the linear algebraic world, we represented this data using a data matrix X and a target vector Y. Okay? And similarly, you have a transformed data matrix Z and a target vector Y. So the target vector doesn't change. Now, how does the linear regression work? It find the weights W tilde, Y W tilde, because these weights only exist in the transformed world, but miraculously, that they allow us to perform a nonlinear to fit with a nonlinear function in the original space. And when we want to predict, we take a point, transform it, and then apply this guy. Okay, so find weights that basically fit the data. Okay, that minimize, the squared error, which is Z W tilde minus Y transpose Z W tilde minus Y. So these are the deviations between the predictions on the data and the target vector on the data, and this is the norm of the difference between the prediction vector and the target vector squared. So the norm squared, so we're minimizing the squared error. Okay, there's a 1 over n, but that doesn't affect the minimization. Okay, and when you perform this minimization, essentially what you're doing is you're trying to get your predictions Z W tilde to be approximately equal to Y. And if Z was invertible, we could just multiply both sides by the inverse of Z, and we would have W tilde is equal to, the inverse of Z times Y. But if Z is not invertible, and that's generally the case because you have more data points than dimensions, okay, it's not even a square matrix. So instead of the inverse, you use the pseudo-inverse. And we call this the pseudo-inverse algorithm. And when Z transpose Z is invertible, Z pseudo-inverse is equal to Z transpose Z inverse, Z transpose. Okay, when this guy exists. Okay, so that's a quick review of linear regression. Okay, and basically it says that, we can efficiently solve the linear regression problem, the fitting problem, in any feature space by pseudo-inverting the transformed data matrix. Okay, so it's a very nice, clean algorithm. Okay, now, this is a feature transform phi, and we're going to be working with the polynomial feature transforms, and I'm going to take this opportunity to introduce you to a particularly nice, convenient, mathematically well-behaved version of the polynomial transform using the Legendre polynomials. So don't panic, it's just the Legendre polynomials. So, we take our vector 1x in, let's say, one dimension, and we transform it to L1 L1 of x, L2 of x, LQ of x. Okay? And so this is the first Legendre polynomial, the second, the third, and so on, the qth Legendre polynomial. So this is exactly analogous to the qth order polynomial transform. In fact, this is a first order polynomial, this is a second, third, fourth, and so on, qth order. So it's exactly analogous. It's more convenient to manipulate these guys than the standard polynomials, and also, they satisfy mathematically interesting properties, mathematically very useful properties, and also visually, they give the right visual of increasing in complexity as you increase the order of the polynomial. So, for example, if you looked at x cubed versus x to the 5, they are both functions that increase like that, and they look equally complex. Not so with the Legendre polynomial. So let me show you what the Legendre polynomials look like, and you can see all the details in the text. Okay. So, the first order Legendre polynomial, L1 of x, is just linear, just like x, okay? And it's a polynomial of degree 1. L2 of x is quadratic. Well, it's quadratic with a shift and a scale, okay? then L3 of x. Okay, this is now a cubic polynomial, and it goes, it has one wiggle. Okay, nice. L4 of x, okay, has two wiggles. Okay, L5 of x. Okay. Wow. And L6 of x. We can even go to L6. It looks like this. Wow. Okay. So what do you observe? What you observe is that as you increase the order of the polynomial, they're clearly getting more complex, intuitively, more wiggles. Okay, so that's nice because we're going to start talking about complexity and constraints and so on and so forth. And now you get the image that if I restrict you to using only the first two Legendre polynomials, so for example, the first two, or let's say the first three, it's considerably less complex than, let's say, allowing you to use sixth order polynomial, because look at the number of wiggles you can introduce by taking linear combinations that involve that guy. Okay. Although technically speaking, all polynomial transforms can give you the same set of functions that you can ultimately implement with linear combinations. Here we see naturally the increase in complexity. There's another very nice property of the Legendre polynomials, which is that they are orthogonal. They're on an orthogonal basis for polynomials, where the inner product is with respect to the uniform measure on -1 to 1. Orthogonal basically means independent, some sort of more formal notion of independence, in the sense that if I tell you to dial down how much of L6 you have, it's not affecting how much of L3 you have. They're sort of independent. And so by telling you to dial down the coefficient of your sixth order Legendre, I'm effectively telling you to dial down this mode in your function, which means I'm telling you to dial down this highly complex mode. If I tell you to dial these guys down, I'm telling you to dial down complex modes and keep only simple modes. So I have a way to control the complexity of a function by deciding how much weight I allow you to put on each of the various more increasing complexity Legendre polynomials. Okay, so very mathematically convenient. Okay, and at the end of the day, they're equivalent to polynomial transforms anyway, so, there's nothing wrong with choosing this more mathematically convenient set of polynomial transforms. And with that said, we'll go back to the general notation using phi. Okay, but bear in mind that, for all of our discussion, we are mostly focusing, we have as a concrete example the Legendre polynomials. Okay, so it's polynomial transforms, for which we can get this nice orthogonal basis that increases in complexity. And with that said, let me introduce you to two hypothesis sets. H2, okay, the second order polynomial fit. So it's h of x, corresponding to the second order Legendre polynomial transform with q equals 2. So h of x, where h of x is equal to w0 plus w1 L1 of x plus w2 L2 of x. And w is in r cubed. So you have three parameters. And h10 of x, hypothesis set 10, which is the hypothesis, the functions, where h of x is equal to w0 plus w1 L1 of x plus up to plus w10 L10 of x. Okay, where w is in r to the 11. So these are just two concrete models. If I wanted to generalize, I could define hq, where the functions are of the form sum from I equals, or from little q equals 0 to big Q of wq L q of x, where L0 of x, it turns out the zeroth order Legendre polynomial is 1. And all these Legendre polynomials are pairwise orthogonal with respect to that uniform measure. Okay, now, here we have the second order polynomial fit. Here we have the 10th order polynomial fit, formally represented as hypothesis sets, okay, with different feature transforms. Now, what should be clear is that the second order polynomial fit, H2, is a subset of H10. What does this mean? What this means is that H2 is a simpler hypothesis set. So, if E in of H2 is approximately E in of H10, so what does that mean? That means that if you had chosen the second order polynomial fit, you get some in-sample error. You fit with the 10th order polynomial, you get pretty much the same in-sample error. Okay. So if the two in-sample errors are comparable, you would be better off having chosen H2, because H2 is simpler. So you expect, H2 fit will be better because it has a tighter link to E out. Again, that's coming from the sort of the VC theory. So if you manage to fit equally well with a simpler hypothesis set, then you're better off. Okay, it's better off to fit with a simpler hypothesis set. Okay, so now what I want to do is show you that, effectively what that means is that if you can constrain the model and fit equally well, then you're better off. So I'm going to translate this into the language of constraints. Okay, and I'm going to show you that H2, so H2 is just a constrained version of H10. Okay? And then that tells us that if you can fit while constraining yourself, you're better off. Okay? Because, we already agreed that if you can fit with H2 just as well, then you're better off with H2 than H10. And I'm going to show you that H2 is a constrained version of H10. So that means if you can fit under constraints just as well, then you're better off. Okay? And here, look, H2 is equal to the hypotheses H of x, which are of the form H of x equals W0 plus W1 L1 of x plus W2 L2 of x plus W10 L10 of x, okay, where W is in R to the 11. And you say, well, wait, that's just the 10th order polynomials, except I haven't put the constraint in yet. So let me put the constraint in. Okay, what's my constraint going to be? And it's, not going to be a surprise. I'm going to require that W3 equals W4 equals W5 equals equals W10 equals 0. Wow. What a pedantic way to write the second order polynomial fit. Yes, the second order polynomial fit is the same as doing the 10th order polynomial fit, but constraining yourself to having all the weights bigger than, so W3 to W10, having all those weights equal to 0. Yes, that's indeed true. Okay, but I'm just trying to make a point here that, the simple hypothesis set is just a constrained version of the more complex hypothesis set. Okay, and now I'll repeat that argument. If we can fit equally well with the constrained hypothesis set, we are better off. Now, this we call the hard order constraint. Hard order constraint. Okay, good. Now, turns out that the hard order constraint is hard to work with. Okay. Now, why do we call it the hard order constraint? Not because it's hard to work with, but because it sort of explicitly sets some of the weights to 0. It's kind of like, it sets it in a hard way. It's kind of like the hard threshold. It's just 0. You cannot deviate from 0. Okay. It's tough to work with mathematically. It's hard to work with mathematically. So, continuing with this philosophy that if I can fit with a constrained hypothesis set, I'm better off. Okay. Let's introduce the soft order constraint. Essentially, let's soften this requirement that the higher order weights should be 0. Okay. And I'm going to define H sub C, okay, which is equal to the 10th order polynomials, H of x. So the 10th order polynomial fit, where H of x is equal to W0 plus W1 L1 of x plus W10 L10 of x, okay, where W is in R to the 11. Okay. And now, instead of explicitly setting some of the weights to 0, that's the hard order constraint, I'm going to give you a budget C. Okay. And I'm asking you to fit while being constrained to not, to not go over your budget. And what does that mean? That means that the sum of your weights, okay, should not go over the budget C. Well, actually, technically, I'm going to require that the sum of your weights squared don't go above your budget. So that any time you decide to add weight to one of the modes, anytime you try to add weight to one of the orders, you're going to pay a price. Okay. And so we want the sum of, from I or from Q equals 0 to 10 of WQ squared to be less equal to C. So I'm giving you a budget. So we call this a soft order constraint because it's not explicitly setting some of the weights to 0. It's giving you a budget. It's encouraging the weights to be close to 0. And it's encouraging all the weights uniformly, saying, I don't care how you fit, but just stay within my budget, please. Okay? And this is a constraint. It's also the case that H sub C is a subset of H sub 10. But now so the same argument applies. Okay, so this is a constrained version of H sub 10. It's a simpler version of H sub 10. So if I can get a comparable fit with H sub C, then I'm better off. Okay, if I can fit equally well with a simpler model, with a constrained model, I'm better off. So now we've linked, constraints to being better off out of sample. And so that shows how if we can, while we're performing the fit, if we can implement a constraint and do just as well, then we're better off. Okay. Now, let me point out that, the soft order constraint is nice in another way, which is that, when you're talking about the hard order constraint, where you set some of the weights to 0, I can either choose H2 or H10. In the soft order constraint, I have a knob C, and I can choose the amount of the constraint, the strength of the constraint. Okay? If I make C go to infinity, then I'm basically recovering H10. So you can think of C as defining the degree of the constraint. So if I had H2 here, and H10, which is the super complex model, okay, then C allows me in some sense to explore this territory. Choosing C allows me to sort of explore models of, varying degrees of constraint. And if I send C larger and larger, I eventually recover H10. C equals to infinity, no constraint. Okay? If I start bringing C smaller and smaller, I'm getting simpler and simpler, coming closer towards H2. And eventually, if I set C almost 0, then I'm even getting simpler than H2 and getting just to the single hypothesis, which is all 0. Okay? So that's the one nice thing about this constraint C. Okay? It allows me it gives me a dynamic range that I can play with. Okay? All right. So, summary. We've linked we've linked fitting with a constraint to accomplishing better out of sample error because you get better generalization, providing you can get a comparable in sample error. Okay, so what's left? What's left is to then figure out, okay, so how do we go ahead and do that? How do we fit under a constraint? Because now we have sort of understood that it's a good thing to do. If we can get a good fit with under a constraint, then it's a good thing to do. Okay, so then the question becomes, how do we do it? So let's erase. Okay, and let me just mention that everything I said doesn't rely on the fact that these are Legendre polynomials. I could put in any feature transform here. So our discussion has been basically general, but we've, made it concrete with the Legendre polynomials. Okay.